In this unit, I'm going to introduce the concept of Brownian motion, which is the motion of a particle of some size under the influence of the random forces that exist in a real environment with sort of thermodynamically active particles. The starting point for this is something called Stokes Flow. So in addition to the random forcing of a particle will resist the temptation to move because there's a drag force on the molecule as it moves. There are different ways to write this, but in Stokes Flow, basically there's a very famous formula that comes out of solving the fluid dynamic continuum equations under the assumption of low Reynolds number flow. And what you find is that the drag force is 3 pi times the viscosity times the diameter or size of the particle times whatever its instantaneous velocity is. And some people, I guess in the original formulation, this was written a little bit differently in terms of the mass and a parameter called eta, which basically has all that stuff baked in. But they're really the same thing. Now, in the real situation, you have both this Stokes flow resistance to flow, but also you have this random forcing from the environment. And you know what this random force really is, like for example, if you're thinking about a particle that's floating around in a gas, that could just be like there's some probability that any particular instant there's a gas molecule that collides with your particle. And bounces off and therefore imparts some change in momentum on your particle. And if this happens lots and lots of times, this creates sort of a random force. And depending on exactly what the environment is, that force can happen a little bit differently. But for the moment, I'm just going to write it as a random force that's a function of time, and we don't really know what that function is because it's random. But we can still write out Newton's law, right? So, F equals ma, and we'll write mass times acceleration equals the sum of the external forces, which includes the Stokes flow resistance to movement as well as the random force. Now, then what I'm going to do is actually try and cast this as a statistical equation. And so what I'm going to do is take the dot product of Newton's law with the position of the particle, and then I'm going to do sort of an ensemble average, meaning that if I was to do this experiment lots of different times with lots of different random forcing functions, what would I expect to happen on average? So let's go ahead and do that. So we'll write the dot product of Newton's law with the position, which I'll also somewhat confusingly call small r of time. So that's the position of the particle with time. So I'll do that dot product. And one thing that'll be helpful will actually be to recognize that the first term in the series can be expanded in a particular way. So it's half of the second derivative with time of r squared minus the velocity squared. If you can't see that, I think it's actually hard to see. I'd encourage you to actually work out by hand that you get back the original front term. All right, then now that we have that written out, we can try taking the ensemble average. So the ensemble average is basically when we just take an average over what would happen for lots of different forcing functions r of t. This is sort of like, capital R of t. So we'll take the equation that we had, and then we'll just take an average over lots of independent experiments. And so basically, because the details are sort of independent of one another, each one of these averages can be done separately. And the key thing is that because the forcing function is random, the last term that shows up in Newton's equation, because it's random is and uncorrelated, has to be 0. Like when I take the average of the forcing and the position, there can be no correlation there, and so that has to be 0. And then if I look at what m times the average of the kinetic, or sorry, I gave it away, the m times the velocity squared. If I want to take that as an average, then I know from statistical thermodynamics that on average, the average kinetic energy, because it has 3 independent components, at least in the high temperature limit, each degree of freedom gets 1/2 kBt energy according to the equipartition theorem, and therefore the average of U squared is just 3 kBt over m. So the ensemble average equation, like if I go back up to the topmost equation, that means that I can divide through by half m times eta, and then I can move the eta, since the eta is not a function of time, I can move it in with the time, and you'll see that that actually makes this easier to solve. So I can write that the second derivative of this newly defined time, newly scaled time, of the positions squared, so the second derivative of that thing plus the first derivative of that thing has to be equal to some forcing function on, some constant forcing function on the right-hand side. In order to solve that, so that's a second order ordinary differential equation. In order to solve it, I need 2 boundary conditions. So let's take a look at what those are. The first one we can get just by defining the starting position of the particle to always be at 0. In that case, r squared at time equals 0 is always 0 because the position is always 0. And the second one I can get by looking at what the derivative of r squared is. So the derivative of r squared, if I evaluate that at 0 and sort of expand what that is, so the derivative of r squared in general is just r times the, or 2 times r times the velocity, and if I evaluate that at time equals 0, just because r is always 0, that means that that cross correlation is always 0. So, if I know that, then I can look for the solution, and the solution turns out to have 3 terms. They all have a prefactor because the right-hand side had a forcing factor of 6 kBt over m times eta squared. But then there's a non-dimensional portion that goes outside, which can be written in terms of eta t. And I've written out the solution here, and you can go ahead and check that it works. So for eta times t much greater than 1, that solution would, the solution, obviously, only the first term of that solution blows up. And so the minus 1 is a constant term, which becomes insignificant for large time, and the exponential becomes exponentially small at large time, and so the solution just becomes the 6 kBt over m times eta times the linear time portion. So that is the solution to the Brownian motion problem. Essentially, if I know the size of my particle and the medium that it's in, so like the viscosity and the temperature it's at, I can actually predict how fast, on average anyway, a particle will get knocked around and migrate through a sample. So this sounds like a really good way to calculate the diffusivity of a molecule or a particle that's in a fluid. So let me try and connect this to the diffusivity next.